Today's speaker is Professor Tony Donné. He got his BS in physics from Utrecht University in 1980 and his PhD in nuclear physics from a Free University of Amsterdam in 1985. From 1985 until 2014, he has been at the FOM Institute DIFFER. DIFFER stands for Dutch Institute for Fundamental Energy Research. First, he was employed as a postdoc. Then he became group leader, deputy division head, and finally he was head of fusion research at the association Euratom FOM. He has held many professional and organizational appointments in the field of fusion. And let me single out just a few of them. From 2009 until last year, he was coordinator of Dutch research activities in the field of fusion research. He has established and he is director of the Dutch-Russian Center of Excellence for Fusion Physics and Technology, and currently he's program director of ITER consortium in the Netherlands. Since 2014, he is program manager of Eurofusion, one of the largest research organizations in Europe. He's also a professor at Eindhoven University of Technology. His research interests are in plasma diagnostics and fusion devices, design and development of diagnostics for ITER. He's co-author of over 170 papers in peer-reviewed journals, over 300 conference proceedings. And finally, let me just stress that the visit of Professor Donné also marks the 10th anniversary of the activity of the Slovenian Fusion Association, an organization which unites researchers in Slovenia in the field of fusion. And although they are not as numerous as their colleagues from the larger countries, they still contribute a considerable part to the fusion research in Europe and beyond Europe.
Thank you very much for this introduction. And well, I'm really positively surprised by so many people in the audience, more people than there are chairs, looks like, although there's still some free chairs for the people sitting there. So in the coming like 45, 50 minutes, I want to take you through the challenges of nuclear fusion. Although I'm working for Eurofusion as an organization, I really think it's much more interesting for you to take you through the overall challenges of fusion, and towards the end of my talk I will say a little bit more about Eurofusion and what we are doing, and especially what the Slovenian research unit, so the Jožef Stefan Institute and the universities are doing within this concept. So let me start you with taking you to some pictures which were introduced by Al Gore. So this is the development of the world population over the years, where since the beginning of the Industrial Revolution you see a very strong increase. And well, for any scientists, and well, I assume you're all scientists, the most interesting part is where the gradients are largest, because that's where the changes appear and where you can do very nice research, and this is where we are now. And Al Gore made an assumption that somewhere the population needs to saturate. It cannot go exponentially up. Somewhere it needs to be saturating. But then if you look at the growth of the energy, you can see that that even goes much faster. And there's in the future a kind of factor of 3 between the energy need of the population in the world and the number of people in the world. And it all has to do with countries like this. This is a picture which was taken by a former colleague of mine, I thought it was Ghana, where the only place for the students to study in the evening is next to the airport, because that's the only part of the country where they have electric light. And so you can sit on one of these concrete pillars and you can study. Of course, these people all want to also have an electric light at home. And so we can expect in the years to come that there's an enormous growth of electricity need in Africa, but also in countries like India and China. So that's one of the issues, but the other issue is that the fossil fuel is quite limited. Now this is what Al Gore showed, that we are now at the peak oil production. Well, I'm never sure when you hear these stories, if you see the predictions of Greenpeace, they're different than the predictions of Shell or British Petrol. Coal, we basically can use still for a few hundred years, but it's very pollutive. And gas, of course, we now have the possibility to go to shale gas, which means, well, chemically not the best method. It's also not good for the environment, but at least it gives energy for, well, at least probably 50 to 200 years. But the main problem is CO2 with all these fossil fuels, and we have to do something. So we need to go to green energy. And this is a picture which I took from the IEA. So here you can see the total world energy consumption, where 80.6% is fossil fuels. This 2.7% nuclear, and this is renewables. But if you look at renewables, about, what is it, 65% of that is just burning of waste. In many Western countries, we burn waste, and the heat which is basically released in that process is used as energy. And they say that's sustainable energy. Well, it's not really the case. And actually the real renewables or sustainable sources are these ones, and that's in the order of 5%. And you can see that what I said before, the countries which are now the biggest energy consumers are China, India, also Southern Asia. We can see also Africa is quickly coming up there. And so in the coming years, we really have to do something on our energy problem. And here you can see what happens. You see there's a large growth of the renewable energies, but at the same time, you can see that gas, coal, oil, they are still growing. So on average, the contribution of fossil fuels to the energy mix are still the same as they were like 25 years ago. We have to realize in countries like China and India, every week they open a new coal-powered energy plant with 2 gigawatt electric. So, and everyone, I'm sure that some of you have been in China for business or maybe for leisure. Well, basically the smog is enormous there, and it's almost difficult to breathe, and that's one of the problems there. So we need to go to clean energy, and there's many different kinds, and I think you all know them: wind, solar, hydro, waves, tidal, biomass. Nuclear fission is also seen as a clean energy because it doesn't contribute to CO2. Geothermal CO2 storage, there's only one missing, and that's fusion. And fusion, that's the energy of the sun. Here you can see a very nice picture of the sun with these nice solar flares. And actually, you could say that almost all the energy we have on Earth is very indirect sun energy, because the sun heats the Earth. It creates, basically, it makes the plants grow. The plants, they basically are the source of fossil fuels. But also wind is basically caused by the sun heating parts of the Earth. Waves, which is a combination of the gravity effect of the moon and the sun. So many of the energy sources we have on Earth are related to the sun. But it's all indirect. And as scientists, you should know that if you are using a process indirect, it's also inefficient. So why don't we bring the sun to Earth? Why don't we try to create a little sun on Earth and see whether we can harness this energy directly? And let me see whether it works. So here you can see the process of nuclear fusion. So you take two forms of hydrogen, deuterium and tritium. So they are isotopes of hydrogen. Deuterium has a proton and a neutron, and tritium has 2 neutrons. So chemically, they are the same as normal hydrogen. Deuterium basically is present in any form of water on Earth. Seawater, basically in this glass, there's some fusion fuel. Tastes very good. Tritium doesn't occur in nature. The problem with tritium is it's radioactive. It's a beta emitter. And tritium has a half-lifetime of 12.5 years. So all the tritium which ever has been present on Earth is gone, and we need to make it artificially. When you fuse these two, you get, during a very short time, a helium-5 nucleus that's so unstable that it immediately falls apart in helium and a neutron. Helium is basically the fusion product. It's not radioactive. It's basically also non-toxic, and it's very valuable. And just for giving you the difference with fission, you take a very heavy atomic nucleus like uranium, you shoot a neutron on it, the atom breaks up into a number of pieces and a lot of neutrons, and you get a lot of energy. And I regularly get the question, how can it be you basically split an atom and you create energy, or you put them together and you create also energy? That's kind of strange, isn't it? Well, it's all in this Einstein ES-mc squared relation, where basically you can see here the average binding energy per nucleon, and the most stable one is iron, which is down here. If you take a heavy atom like uranium and you split it into smaller pieces, actually you lose energy. You lose mass and you gain net energy. And the same is with fission of hydrogen. And you can see that it's much steeper here. So thinking about the gradients, this is where the interesting part is. And you can generate really a lot of energy by fusion of hydrogen. To give you an indication, if we succeed to create the fusion process on Earth, for a 2 gigawatt electric reactor, we need 500 kilogram of fuel, 250 kilogram of deuterium, and 250 kilogram of lithium. Both are non-radioactive, so you can just put them in the trunk of your car, you can drive to the reactor, and then at the end of the year you have basically like 500 kilogram, or a little less, of course, because you lose mass. So maybe 480 kilogram of helium, and you created a lot of energy. So it's very useful, but we have to make it work. And this is why some countries, where I see Europe as one country, but also US, Japan, you can see all these countries which basically have a lot of light during the nighttime. They want to create fusion because you don't contribute to the global warming, you don't release CO2, it's clean, it's also very safe, as I will explain later. The fuel is deuterium, which is basically just all this black stuff here. So you can take it out of the water, you can do that very cheap. And lithium, we need to basically breed the tritium. There's also not a problem with weapons industry, so no proliferation problem. There's only one difficulty, and that is fusion is impossible. So this is it, you can go. I'm a scientist, so for me nothing is impossible. If people say it's impossible, I basically translate it into it's very difficult. It's not impossible because it's working already on the sun. We know it's working. And, but how to do that now on Earth, and what are the problems? So let me now take you to a number of these challenges. Well, first of all, in the sun, the process occurs at a temperature of like 15 million degrees. And in sun, the gravity is very strong and very high. And so the particles are very close to each other. And the problem is that actually the positive nuclei of deuterium and tritium, they repel each other. And we need to give them enough energy that when they meet, they have a chance to fuse. And so the sun, 15 million, but if we do it on Earth, where we don't have the help of gravity, well, just a little bit, but not that much, we need a temperature which is a factor of 10 higher to still give the particles enough energy to fuse. It's all shown in this diagram, which shows the reaction probability as a function of temperature. If you want to have it in degrees Celsius or Kelvin, just multiply by a factor of 11,000, the Boltzmann constant. So typically you can see that the reaction probability for deuterium and tritium is highest, but it's also at the lowest temperature. Deuterium would be also possible, but it peaks at much higher temperature. Or deuterium-3 helium would be a possibility. But there you have the problem that 3 helium almost doesn't exist on Earth, so you have to go to the moon to basically mine your helium. So that's why we are focusing on deuterium-tritium. We don't have to be in the peak of this diagram, so already at a temperature of about 10 keV, which corresponds to well, roughly 100 million, 110 million degrees, you can already have enough fusion reaction. That's just because of the quantum mechanical tunneling effect. So what are now the challenges? So let me see, this is basically the ITER reactor, which I will, towards the end of my talk. And the challenges are really, well, how do we create a medium, a plasma? I will explain what a plasma is in a minute, which is 10 times hotter than the sun. And so when you create something which is 10 times hotter than the sun, how on earth do you contain it? Because if you have it in a material vessel, it could melt the vessel. So we have to basically try to have a kind of solar flare. Well, this is on the sun where these structures are like tens or maybe even 100,000 kilometers in diameter. And here you can see already the principle we are using. Actually, the magnetic field of the sun is bending the plasma back. And we are using magnets also to try to basically confine the plasma. Then what everyone knows that if you make something very hot, and at the edge where you have your material, it's cold, you have very high gradients. If you have high temperature gradients, you get turbulence. And turbulence is basically not very good for your confinement because you lose energy. So we have to solve that. Then we are creating, well, in ITER, the device which I will explain, we basically have 500 megawatt of fusion power. In the ultimate reactor, it's 2 gigawatt. We have to take this heat out. So we need to develop materials which you actually could lay on the surface of the sun. So materials which really could be at the surface of the sun and then for years without melting away. Of course, we have the big advantage in a fusion reactor that we can get there with cooling channels. So we can cool with water, with helium or whatever, which at the sun is a little bit unpractical, of course. Then we have the problem, there's many neutrons in the fusion reaction. The neutrons, they give ultimately the electricity because they heat the blanket and they also create the tritium in the blanket. But at the same time, you need to be very careful because you have like superconducting coils here, which are at 4 Kelvin. And like 2 meters away, you have a temperature of 150 million degrees. So you have to develop super materials. And then the other issue is the tritium. I mentioned tritium doesn't occur in nature. You have to make it. You can make it in the CANDU reactors. Most of the world supply of tritium is in Canada. So when we start a reactor, you have to bring tritium, but when the reactor is working, it should try to maintain its own quantity of tritium. So that basically net, you are basically running this process, and you start with like 10 kilograms of tritium, and then after 30 years, when you stop your reactor, you still have your 10 kilograms of tritium. And then I think one of the biggest challenge is that ITER is a very big international project with many political aspects. It has 15 million components which are put together. And it's yeah, really a huge challenge. And I think at the moment it's more the politics which is determining the timeline than the science. Okay, let me now take you through this challenge. How do we make something 10 times hotter than the sun? Well, it's actually very simple. I take a vacuum chamber, a vacuum tube. I fill it with deuterium and tritium gas, well, both components of hydrogen, so they're all blue. And then we basically have to heat it. And well, one method of heating is basically using like microwaves, radio frequency heating. And when you put the heating on, then at a certain temperature, the atoms in the tube, they fall apart in ions and electrons. So and that's what we call plasma. A plasma is a fully ionized gas. So basically the plasma is quasi-neutral because there are as many electrons in the tube as there are atoms. I recently gave this talk in a school, and then they said, well, there's two more ions than electrons. But then I said, well, two of these electrons are hiding behind the ions. So, but in principle, it's quasi-neutral. And they are charged particles, and this is very important. Well, there's many plasmas on Earth. This is, I think, the most beautiful plasma you can see on Earth, the aurora borealis in northern Europe. But there's many other, like the interior of lamps or flames. They're all plasmas. They sometimes partly ionized, but in many cases ionized gases. I will take now another challenge immediately also, and that's how we basically can now try to confine this. Well, this is what happens if you put the heating high. So all these particles in this vacuum chamber, they get a lot of energy, they start to move faster. But the problem is if you don't do anything, the particles, they will hit the walls and, well, basically they lose their energy. The wall, they will get slowly warm. So we need to find a trick, and the trick is the magnetic fields, because if you apply a magnetic field, in this case in the longitudinal direction, all the particles, they line up and they make a kind of spiral motion around the magnetic field lines. So now they cannot hit anymore the sides of the tube. Of course, you see immediately a problem that they run out at the end of the tube. So the solution is to bend it around in a torus, and this is actually giving the best confinement. And I have a little animation hidden behind here. Need to make it larger. This is what happens if you basically don't have your magnetic field on. All the particles, they fly basically away. If you turn the magnetic field on, you see the particles going very nicely along the field lines. But you see also that we get a charge separation. The electrons, they go up, and the ions, they go down. And this is an effect which we don't like, because this gives an electric field which then has the tendency to push the plasma out to the wall. So to circumvent that, we basically apply a plasma current in this direction, and the plasma current generates a magnetic field in a small direction. And in total, we get a helical magnetic field line. And now the particles, they stay mixed. We don't have any problem. So with magnetic fields, we can confine such a hot plasma. It's like a magnetic train, or, well, I think several of you have seen the Meissner effect, where you have superconducting materials which are floating. Actually, we use the same principle, and it works. So, okay, I basically now explained how this hot plasma can be confined, but how do we get it hot enough? Well, also here I have a little animation. We have the plasma current. I already indicated we make a plasma current to make a magnetic field. A side effect of the plasma current is it also heats the plasma, and you can heat it to 10 million degrees just with a current. Of course, it's easy to get a very high temperature because the plasma is very dilute, so the density is very low. But additionally, you can use microwave radiation. I already mentioned that. You can either launch radiation, which is resonant with the electrons or with the ions. They get higher energy, and they start colliding with their neighbors in the plasma, and you basically create higher temperatures, or neutral beams, where you use neutral beams because if you use an atom beam or ion beam, you never can get the ions through the magnetic field. So you first need to neutralize, and then you shoot the particles in. And in this way, you easily can create temperatures of like even up to 400 million degrees. No problem at all. We do that like quite regularly at JET, which is the biggest experiment in the world. Well, 10 kV we reach quite often. 400 kV, that's like some record shots, but the temperatures for fusion is very easy to achieve. Here you see a picture of JET, which is the Joint European Torus. So some of your Slovenian colleagues are working there. And you can see one of the neutral beam systems. So here are the ion sources where you create the beams. Then you neutralize them in a gas chamber. You bend away particles which didn't neutralize because you don't want to have them to hit the walls here. and then the neutral particles are injected into the plasma. In Eurofusion, we are concentrating work on a number of devices. JET, by far the largest one. TCV will be, this in Switzerland, in Lausanne, will be taken aboard this year. Master upgrade will come online next year. It's now under upgrade. And this is a, well, very artistic view of Aztec's upgrade, which I like as a picture, but it's very difficult to see how the machine is oriented because they use this fisheye lens, but it gave them the picture of the best science, the prize of the best science picture in the year. ITER will come online in like 10 years from now, and together with Japan, Europe is working on GT60SA in Japan, which will come in operation in 2019. So these are the main devices where we're doing work on. JET, well, here you very nicely see the vacuum vessel, the transformer yoke to induce the current. You can see the toroidal field coils here. These are also coils which are all needed to keep the plasma nicely in its position. This is the interior, so it gives you an idea of the size. This is still a relatively old picture of JET when JET still had carbon tiles, so you could send a man with basically just a white suit. At the moment, the interior of JET is completely clad with beryllium-coated tungsten tiles. And because beryllium oxide is toxic, you cannot send simply a man in. He needs to be in a kind of spacesuit. And here you can see a kind of overlay with a plasma. This is actually a plasma having a temperature of 12 keV. Interesting is to see that from the center of the plasma, you almost don't see any light. And the reason is that the particles are fully ionized, so you don't have line radiation from the core. So the only radiation you see is from the very edge, where the temperature is much cooler, and that's where the ionization processes basically occur. And then, of course, in the bottom part, which we call diverter, you also have a lot of radiation, which is partly because these components get hot, but partly also because there's a lot of ionization processes, recycling, etc. And here we have a little movie of MUST, which is a small spherical tokamak. We can see also very nicely the edge of the plasma. You see these instabilities, which are helical, which are aligned with the magnetic field. And these are already some of the instabilities which are, well, being nasty. So we have to control them, we have to harness them. Okay. Let me now take you through 50 years of fusion research. This is what Bosjan taught me, that fusion journalists always say, well, you're working already 50 years on it and it's still 50 years to go. So you're getting nowhere. I will show you that this is not really true. We really did a lot. If we start now in the 60s, we started with a lot of different concepts, like the linear concepts, mirror machines. We had all kinds of devices like this cusp. This is the first tellerator, which was introduced by Lyman Spitzer. So he didn't think about the solution with the current in the plasma, but he basically made this figure 8, which basically also is preventing this charge separation between the electrons and the ions. But still we had a lot of problems. But in the late 60s, the Russians claimed that they had a device which they called tokamak, and I probably, from your historic relation with Russia, I think you probably can all read this and know what it means. For me, it's much more difficult to pronounce, but the tokamak was a concept where the Russians said, well, we can reach temperatures of typically 1 to 2 kilo electron volt. And everyone in the world was struggling to get temperatures of like 100 eV, 200 eV. No one believed the Russians, so a team of British scientists went in '68 to Moscow. They went there with a very precise temperature measurement. And they came back with the conclusion, well, the Russians didn't tell the truth. And, well, yes, it's the Russians, of course. And then immediately the English said, well, yeah, but the temperature was much higher than what they claimed. It's actually the other way around. So they were really conservative. And so immediately at that time, all in the world, people started to build tokamaks, small ones and later bigger ones. And then in parallel, still some activities like this one is Wendelstein 7X. This is actually a kind of evolution of this figure 8. It's a stellarator where by specially shaped coils you want to confine the plasma. So this is a currentless plasma, there's no current running, you're only using external coils to confine the plasma. All these coils are superconducting, and this device, I think I'll come back to it later, will come in operation later this year in Greifswald in northern Germany. This is a device in Japan. It's beautiful. I've been once in this device. It's about 1.5 meters high here. You can stand in. It's like a very big kind of helix. And they can create already quite high temperatures. And the important advantage of these devices is that you can create a continuous plasma. Not a pulse one, but continuous. This is the device where I showed a little movie of Mast in England, which is a small spherical device. So where are we now? If we look at the largest device now, JET, we are here, and we call that break even. So the fusion power we create in the plasma is equivalent to the input power. That's already quite good, and these devices are built to understand the science. What we are building now is ITER. Come back to ITER. Here's the man to scale for ITER. I before showed you the man in JET, so ITER is a little bit bigger. And ITER is designed to have a power gain of a factor of 10. So the fusion power is 10 times the input power. And that's very important because the fusion power, 80% of the power is carried by the neutron and 20% by the helium. The helium is charged and stays in the plasma. So the helium particle should self-heat the plasma. So it should give its energy to the plasma. So in principle, you get here in the regime where the plasma particles have enough energy to heat the plasma. Of course, you always have to fuel the plasma. Good. Now the third challenge, thermal insulation. And what we did in the early years is you have the heating power, which we first everyone used the plasma current, the stored energy, and you get a temperature profile which looks like this. So you get like 2, maybe 3 keV. And then the idea was we want to go higher. Well, the problem is that with the current, the plasma becomes very, very well conducting. So the dissipation is basically disappearing. And so the idea was what happens if we put in more energy? And what we noted is, well, we can use this radio frequency heating, we can use neutral beams. And what we saw is we see a saturation. So the energy doesn't go up, but it saturates. And well, we get some higher temperatures, but it's not really enough. The problem is all this turbulence, and you can well this is the result of a calculation, and the calculation gets unstable when you go to the very center of the plasma. So that's why there's a hole in the calculation. But of course, the plasma is continuous. But all these cells, you can see that a particle which is here, which is a hot particle in the core, via a turbulent cell, can run very quickly outside. And you lose it. And I can show it here. I have this calculation done by a group of Princeton, where you see the plasma, you see these turbulent eddies. Here you can see a cross-section through the plasma. Very long stretched turbulent eddies. So particles from here, they are immediately lost to the outside. And what they did now in the calculation is they gave the plasma a different velocity shear at different layers. So they let the plasma rotate with different speeds. And what you do there is you tear actually the eddies apart. And this is very good for the confinement. You get a much better confinement. And you can induce a velocity shear, for instance, by putting in neutral beams tangentially to the plasma. And people did that in the early 80s in Aztecs in Munich, gushing. And they found that basically they can go further up before it saturates, and also you can see the profile, it's higher. The green and the red profiles are almost the same. You see the main distinction is here at the very edge, where you have this very steep barrier. Well, this we immediately called H mode, high confinement mode, and the green one was called the low confinement mode. And this is called a transport barrier. So what we did here is we created a transport barrier at the edge by putting in a differential rotation of the plasma. And then much later in the mid-90s, we succeeded also to doing similar tricks to the core plasma. And now we can reach temperatures like 12 keV, which are needed for fusion. So you really can reach much higher temperatures. At the same time, we're using like radio frequency heating to kill instabilities. Well, jargon is that we call it sometimes an island. Here you can see a plasma, you create an island. This is artificially created, but in a plasma they can also arise spontaneously. And then at this moment we turn the gyrotron on, which is a big magnetron, and you can suppress the instability. And this is a control system which has been developed. I understood that also here in the Josan Stefan Institute you're doing control engineering. So here you're using also gyrotron. Power is 1 megawatt. You basically blow it in the plasma and the energy is absorbed by the island. There's also some radiation coming back in the same frequency band. So basically you try to measure this radiation. The only difficulty is this is measuring nanowatts, this is megawatts, and you really should be careful that not direct radiation from here is coming there because your radiometer will be immediately evaporated. So you have to do your very best with dielectric plates and notch filters to really try to get the direct radiation down, but it works. And this can then be used to stabilize these instabilities. So I'm not going to explain all the details, but the blue signal is the instability here. And then at 3 seconds, we turn on the gyrotron, and you can see that within like a few milliseconds, the instability is completely gone. So this is very nice because you can really try to act on individual turbulence. So it took you now to 3 of the challenges, which is most of my story. The other ones I take you much faster through, and I think we solved all 3 of them, so that's good. So where are we now? And well, talking about these 50 years, what did we do in the meantime? Well, here you can see the power multiplication factor, starting from the first tokamak T3 in Moscow from 1968 to JET, and you can see that the power multiplies or doubles every 1.8 years. And just for comparison, this is Moore's law for transistors with the doubling time is every 2 years. Well, everyone knows when you buy now your iPhone 6, at the moment you basically know how to use it. Apple is already with the iPhone 7, which is even better. And the same with Samsung, it doesn't matter. Anything you buy or laptop, at the moment you know how to use it. Basically there's already something better. And we all think it's going so fast. And this is even going faster, but people don't realize. One of the problems was that in the early 90s, we had a design in Europe to build a machine at that time called NET, the next European tokamak. Should come up operational in 2005, but the oil price was low. America and Russia decided to work together on the ITER project. So this was the time of glasnost and perestroika. Reagan and Gorbachev, they had some meetings. The ITER project was started and the European politicians said, well, forget about NET, don't build it, work on ITER. So immediately 10 years of work was basically put in the basement of the building where I'm now, still there. So we lost a number of years. Then in 98, the design was ready of ITER and the Americans found it too costly. So we had to work on a smaller design. It was finished in 2001. Then we had to decide whether we would set up the ITER organization. It has taken 3 years. Then we have been talking like 3 years on where to build it. So there was a very long impasse between Japan and France. That was resolved. And then they set up the ITER team in a very politically complicated way. And the reason is that now, for political reasons, ITER is coming in operation, well, basically in 10 years from now. Let me take you quickly through the other challenges. The material loads. So typically in the ITER diverter we have 10 megawatt per square meter. The highest which I could find in other fields in space science is, for instance, the heat loads during the re-entry of a space vehicle, which are typically 3 megawatt per square meter. Transiently, the heat load in the Ariane 5 rocket is 85, but transiently during these modes in the edge of a tokamak, the edge localized modes, you can have 2 gigawatt per square meter, and you have to cool that. So we really have to find ways to harness that. And the problem is really that if you take the cross-section of a fusion reactor, in the inside you create 500 megawatts, which you need to basically exhaust. So all this heat is coming out as energetic particles, and they cross then a certain layer, which is your last closed magnetic surface. So all the magnetic surfaces in the center, they close upon themselves. So particles are pretty well confined. But as soon as they cross this brown layer, they basically lead to the diverter here. Well, the thickness of this layer is 2 centimeters. 500 megawatt, and if you basically make just the geometric calculations, you find the power density of 1 gigawatt per meter square. That's 100 times what you have in the surface of the sun. So no way you find a material which can withstand that. So what you can do is you can choose some geometrical choices that the field lines in the diverter, they have a grazing incidence on the surfaces. We can also puff in gas, so that a lot of the particles which are coming to the diverter, they lose their energy by collisions. And in that way we can get typically down to 10 megawatt per square meter. And that's good, because that's still doable. And we are studying various concepts. So this is in TCV in Switzerland, where we are basically studying the snowflake diverter. Where we split basically the plasma in a number of lags, so spreading the energy over a larger surface. And in England, at Master Upgrade, they have a Super X where they do the same. They basically try to spread the heat load over a much larger surface. At the same time, we're doing also research in liquid diverters, because if you have liquid diverters, you can continuously replenish the material. And there's a lot of efforts going on in many different fields. So there's some diverter simulators. This is in the Netherlands in my former lab. It's in Jülich. So these are plasma simulators, diverter simulators. There's an electron beam facility in Jülich as well. And West, which before was known in Tor Supra in Cadarache in France, is basically a tokamak which is used for testing tungsten. Here you can see what happens if you basically play around with the plasma. This was a deliberate experiment in MIT, Alcatar CMOT, with molybdenum tiles, where they really had the plasma to hit the wall, and you can see there's a lot of melting, which you basically need to prevent. The problem is if you basically take away material somewhere, it basically gets on other places of the plasma, so you grow this kind of structures. Was in texture, this is carbon, so you get these kind of beautiful structures to look at, and I think for material scientists it's really fascinating. Of course, for fusion people it's a nuisance. Well, especially for diagnosticians as me, it's a nuisance because you get these layers on your mirrors and you can't see anything. I think this is a little too detailed. Well, this is the diverter. So here you can see the diverter. It's built in cassettes. This is the component with the shortest lifetime in a reactor, so you have to replace the diverter typically every 2 years. And well, here you can see a cassette. It's actually put on a rail structure, so you can shift in the cassettes from one side, you can rotate them all around, and on the other side you can take out the cassettes you want to replace. So in this way you can quickly change these cassettes. Ultimately in a fusion reactor you want to do that in a few days' time. And here you can see a mock-up. So this is the typical size. It's pretty large, it's 1 meter. This is a carbon diverter which is cooled, actively cooled. And here you can see some testing. This is from my former lab where they have a plasma gun where they can typically create 10 to 30 megawatt per square meter. And they are now going to also make a superconducting device where it can be done basically 24/7. So you can really expose materials for a very long time. And well, here also you can see the trick where you try to decouple the plasma from the edge by putting in gas, and you can also have a bias which basically prevents the plasma from directly interacting. That's also a way to try to protect your materials. I'm not saying much on the neutron bombardment. The fluxes in ITER, they're much higher than in the best shot we ever had in JET, which is already like almost 20 years ago. And if you compare it with the fission plant, so ITER is here. We are talking always about radiation damage in the number of displacements per atom. So every atom in the surface of your reactor in ITER will be displaced like 2 times, 1 to 2 times during the lifetime. In the ultimate fusion power plant, we're talking about 150 times. So we really need to develop materials which are robust. We are not alone there. Typically, generation 4 fission plants, they are in the order of 100, so basically from 50 to 100. So we are doing also quite many co-developments with fission people. One of the important facilities we're working on is the International Fusion Materials Radiation Facility, which is a large deuterium accelerator, where the deuterium ions, they hit a lithium target, which is here, and then we have a test cell, and in the test cell we can then test various materials. Like here we are creep testing various metals and to measure their strength after exposure to neutrons. Tritium, I have only one slide on that. The problem is that we need to create the tritium in the reactor. The idea is that we use the fission of lithium-6. So a neutron hits lithium-6, it gives helium and tritium. The tritium we basically feed back into the plasma, and the helium is basically, basically it's a very valuable exhaust product. And the way it works is we have a blanket where there's a liquid of lead lithium. It's a eutectic mixture. It's a fluid, it's flowing through, and basically each time the neutrons hit the lithium, they basically create a tritium. And well, the idea is that we should create exactly as much tritium as we use. Actually, the best would to be create a little bit more. If the tritium breeding ratio is less than 1, if it's for instance 0.96, basically the cost of electricity from fusion will increase by a factor of 2. So it's really important to be just above 1. And then I think the challenge, and this is the more easy digest part of my talk, ITER, 34 countries, 15 million components. This is how the device will look like. So you can see the core of the tokamak with the diverter, the magnetic field coils. And I can show you a little bit how this is going. This is a more detailed graph with the vacuum chamber. Here you can see the diagnostic port plugs. So a lot of measuring equipment is put in these port plugs. The diverter you can see the pumps. So a lot of cooling tubes. This is the complex. So this is the headquarters building that's already finished. This is the tokamak complex. This is the building where they built the largest coils. The largest coils are 30 meters in diameter. And you cannot, let's say, make them anywhere in the world and then transport them to ITER, because it would be impossible. You cannot get them over the road to ITER. So the largest coils are actually made here. This is the cryogenic lab, diagnostic labs, etc. This is the ITER building, many floors. The total height is in the order of 60 meters. Here you can see the first building. This is the base mat of the tokamak. So this is actually the ground floor. This is the visitor building where the architect had some creative moments. It's a very ugly building, but some people like it. This is the first building which was ready. It was the building for the Pelowidal field coils. This is the headquarters building. This is the Pelowidal field coil building. So this is like 200 meters, like 2 soccer fields long, 60 meters wide. So you could play 2 indoor soccer games here at the same time. And ultimately there will be 6 of these coils. Well, 5 of these coils will be manufactured here. Here you can see the seismic plinths. ITER is built in a seismic area, and so this means that the building is isolated. So what they do is they have these plinths which are 1.5 meters high, then they have steel plates and rubber here. There's 483 of them. Here you can see actually the structure. This is the center of the tokamak. And ITER is built in a box in a box. So the ITER building is actually standing completely isolated in a separate building. And it can withstand the earthquake with a magnitude of 9.5 on Richter scale. And I think the highest they ever had in this area was 7. But it's kind of safety measure. Here you can see they are lying the basement. And I gave this talk also in my daughter's school, so I had to put in some things to entertain the public, but sorry, forgot to take it out. But this is the center of the tokamak, and well, here you can see some of the more recent pictures of ITER. The vacuum vessel, it's a double vessel, 6 centimeter thick vacuum vessel, and the weight is more heavy than the Eiffel Tower, so 1.2 times the Eiffel Tower. The coils, superconducting coils, which are made in many countries in the world, and typically the one toroidal field coil of ITER weighs the same as a fully loaded jumbo jet. So it's really, we're talking about big things. Here you can see the radial plates. So these are plates in which the coils are positioned, and they need to be very well strengthened because there's very strong forces on the coil. Here you can see the winding. This is still testing where they wind the coil. This is how they put it together. So this is the area where they assemble the coils in the vacuum vessel. And again, a little man to scale. Here again. This is the cooling system. So just to give you an idea of the cooling channels, how complicated it is. This is the cryogenic system. Well, all the coils are helium cooled. This is one of the radio frequency antennas. So this is ion cyclotron heating and current drive, where you can see also the antenna with all the matching networks in there. Neutral beam heating. ITER has 2 neutral beams, but they have a provision for a third one here, and then they have a diagnostic neutral beam here. So actually there's 4 ultimately. Heavy loads. ITER is like 80 kilometers from the sea. So many of the components, they arrive at the harbor of Marseille, and then they need to be transported with these kind of heavy loads. For the most heavy components, it takes 4 days to travel from the harbor to ITER. And they can only do that during nighttime because there's not much traffic. Also, they need to, for instance, there's some viaducts on the way, and they basically can take away the complete viaduct with a crane. The convoy passes, and then they put away the viaduct. They took away roundabouts on the route, so in a sense, these things are very popular with the local population because now the streamlining of the traffic is suddenly much better than it was. So here you can see the first test convoy. ITER is a project in which all these countries participate. It will be built in Cadarache in southern France, and it's basically 15 billion euro. It will be first experiments. It's a little unsure, but it's about 24. It delivers 500 megawatt of fusion power. It delivers not electricity yet. But the input power is 50 megawatt. And after ITER, we are working on demo and on the fusion power plant. And I think I have, with that I think I addressed all the challenges which we have, where we hope that ITER and IFMIF will help us to answer some of these problems here. And I just want to give you like, I think 5 more slides on Eurofusion. So Eurofusion is actually, geographically, it's the largest research organization in Europe because we have most member countries. In that sense, we are larger than CERN or ESA or ESO. 27 countries, 29 members because Germany has 3 members. Unfortunately, we're not the largest in budget, so that's there CERN and ESA are definitely doing better. Well, you can see here some of the task force leaders which are coming from different countries, and well, these 2 are stationed in Garching. Important for us is the fusion roadmap. So we developed a roadmap which basically the ultimate goal is to deliver electricity by 2050. We have defined challenges which are slightly different from the ones which I mentioned today, but very much related. And for each challenge we have seen what is the present status, what do we not know, so what are the unresolved and urgent issues. We made a research and development plan and estimated resources, and then we are basically trying to follow this roadmap. And these are our challenges. So plasma operation, that's very close to my first 3 challenges of today. Heat exhaust, that's on the materials, which you can put in the sun. Then this is very much, number 3 to 7 is very much on developing the demonstration power plant. So neutron resistant materials, being able to create enough tritium. Of course, safety is an important issue. Demo design, and we want ultimately fusion to be competitive. So the cost of electricity should be not too high. And number 8 is stellarators, so this very complicated factor of 8, or the thing with the complicated coil, it's our backup strategy. And well, basically we group it here, but let me split here. This is how we are organized. So we have one big department which we call ITER Physics, but we have 2 branches, ITER Physics in Kalm, ITER Physics in Garching, with different work packages. Sorry for the acronyms, but I learned today that you have also acronyms like F4, F5, K2 and whatever. So we are not different. And when I would spell it out anyhow, you wouldn't have time to read it. Then we have PPPT, the Power Plant Physics and Technology. That's actually the demo design, and we have the Program Management Unit. And you can see I highlighted all the areas where Slovenia is active. I think you're most active in the JET, in the PFC, and also in enabling research. That's really where, let's say, a large part of your activity is going. But also a number of the other ones like co-development, medium-sized tokamaks, and materials. There's quite some activities. I should mention, I forgot to put here the Fusion Expo, which of course is a large activity of the Slovenian Research Institute in the past. And this year, one of the highlights is the European Fusion Program Workshop, which will be organized in December here in Slovenia. This is how we are organized. So I'm working, fortunately, with a number of people. So the 2 science heads are Xavier Litedon, ITER Physics, and Gianfranco Federici doing the demo design. We have a deputy, Darren MacDonald, in Garching for the ITER Physics in Garching. At JET, we have Andrea Morari. Of course, we need administration, we need communications, very important, Petra Nixon. And at JET, we have Lauren Horton. So the new system with JET is that JET is paid directly by the European Commission. Lauren Horton is responsible for running the device, and we are responsible for organizing the scientific program. So it's a kind of natural kind of combination. That brings me to the end. Sorry, I took a little bit more time than your usual 45 minutes. If there's questions, I'm happy to answer them.